So should I start?
Her voice is not audible.
Sir, we are unable to hear you.
Am I audible, sir?
Yes,
Yeah,
sir.
you're audible now.
Yeah, sorry for the little bit technical issues. And without late, I am very much privileged to introduce today's session speaker, Professor Devdut Sheet from IIT Kharagpur. Devdut Sheet, sir, is an assistant professor of electrical engineering at Indian Institute of Technology, Kharagpur, and founder of Skin Curate Research. Sir received MS and PhD degrees in computational medical imaging and machine learning from the Indian Institute of Technology, Kharagpur in 2010 and 14 respectively. He was a German visiting PhD scholar to TU Munich during 11 and 12. Sir research interests include deep learning and domain adaptation, computational medical imaging, and multidimensional signal processing, surgical analytics, and informatics, visualization, and augmented reality technology design. Sir has widely published in journals including medical image analysis and conferences like the IEEE International Symposium on Biomedical Imaging. He is a member of IEEE and other distinguished professional bodies. Sir is also an editor of IEEE Pulse since 2014. And on behalf of University College of Engineering, I welcome you, sir, to this online 5 days FDP for this session, sir. Over to you, sir.
Thank you. Thanks for inviting me and having me over here. It's a pleasure always to come and speak on this topic, which is really dear to my heart. Now, given that the theme is exactly on medical image analysis, so I thought of, so one was trying to do a very cliched getting started thing with a keynote on why you should do medical image analysis. But I believe that over the last 6-7 years that I've been going around the country and also do a lot of parts of the world and trying to do the same kind of a keynote on emerging economies where people are supposed to now start at least with medical image analysis. What I believe is the next biggest economic boom. And at least in 2020, we have seen exactly the forecast pretty much coming true. Maybe for COVID or whatsoever, I don't know. But then we also need to understand that COVID is not just one single phenomenon. There have been other viral and epidemic outbreaks we have been facing every 2 to 5 years. Before that, somehow like it got a major marketing prominence and dominance, which was not so attributed to other diseases which we had in the past. Nonetheless, but then whatever you saw on medical image analysis getting rolled out as a diagnostic service in this situation of exigency was all based on what was done much ahead of time. And in the previous 5 to 10 years ago, what we had been doing, they are what is bearing the fruits. So today, medical image analysis is no more a thing which is only of research, but to a significant extent, this is something which gets into production. You have products getting built up, and they are really getting pushed to be used in a good way. Now, on that line, I thought of doing something which is of prominent interest in today's world, where you know that you essentially need data and more quality, more amount of very reliable data and very high quality data in order to be able to get any of your at least vision or even speech or language based algorithms built up. The problem over and over is getting access to such kind of high quality data. Now for general vision, where you're looking at identifying cats versus dogs, it's much more easier to get access to say good quality data, because you will have humans who are just annotating them. The problem is that when you're looking at medical images, you need specialists. You cannot just have a generalist who is going to do that. So just somebody who is on a computer and has a lot of time cannot sit and start marking say liver tumors, because you need some sort of a domain expertise in order to be able to spot them and then mark them. So these are definitely challenges which are there. And today, aptly on the same lines is what I would be speaking about. So what happens when you have very weakly labeled data set, and how do you really go around with doing deep learning for medical image analysis with these weakly labeled data set? Otherwise, it becomes really a big problem. Now, at the start of it, I have a lot of conflicts to disclose, and these are what I need to do always legally. Just let it run over. Okay, so these are people who have funded at some point of time, and all the work which I am presenting over here is in some way or other based on the generous support which all of these agencies have done at some point of time. Now, coming to the fundamental definition, and because I do a lot of machine learning based medical image analysis, I always draw this one. And at this particular point of time, I will also put a disclaimer over there that it's not that medical image analysis can only be done with machine learning. So please don't be under that impression. There is a whole gamut of things which we can do without using machine learning at all. And in fact, because I'm more of an image analyst, so I don't restrict myself to a certain tool which I have in hand. I am open to any of those, and the general success is that don't restrict yourself to only machine learning, and that machine learning is not the solution to all problems on earth. Now, the point which I have over here is something like this, that say we are looking at this very basic definition of machine learning, then it's according to Tom Mischel. What it says is pretty straightforward, that the task which we are looking at certain activity which is called as learning, and learning will happen with respect to a certain thing which is called as experience, and let us attribute a certain variable E to experience. Now what it says is that you will be learning to perform a certain task T, and you will be measuring the performance in performing that task with a performance measure which is called as P. And what will happen is that if you are learning, then you would see that the performance P as measured for the task T keeps on improving with experience E, and that is like really critical. So in case of learning, this is something which I would really like to put forward over here, that it's really critical that we understand this part, that a computer program is supposed to is actually said to learn from experience E with respect to performing a certain class of task T, and the performance measure, which is measured in terms of P. And what you would see is that the value of P will keep on increasing as and when you will have an increase in E. And all of this keeping in mind that you have a task T in hand. So if we try to simplify this one, it is something like this, that say a student is studying in a class of history and is writing more and more exams of history. So the more and more tests a student of history takes, the more is the experience the student gaining. And if the student is actually learning, then the marks of the student should keep on increasing over there. So that is the performance measure P. So if marks increase, then P increases. With more and more tests that the student is taking, then E is increasing. That's why P is increasing. Then you would say that the task is essentially understanding history and being able to respond to questions related to history. That is the task. The student is able to learn history properly. The other side of it is that in case you see that more and more exams a student is taking, the marks are going lower and lower. So what it means is that E is increasing, but P is decreasing. So as the performance measure P keeps on decreasing, while the experience E is increasing, then the student is not learning anything. Okay. With respect to a certain task. Now the other side of it is something like this, that you expose a student to the syllabus of history, but you ask the student to write a question paper in geography. In that case, what you are doing is you wanted to do a certain task, which is write a question paper in geography, but the experience which you are giving to the student E is in history. So the experience and the task are unrelated over there, and that's the reason why the student will not be able to work. So the same thing holds true over here as well. So in case of any machine learning based measure, you need to keep in mind that the experience has to be gained for performing a certain task. If they are unrelated, then it really does not make any sense. So what I'm going to speak today is with respect to these 4 papers, which we had recently published, so between 2018 and 2020. And then I'm going to take it even further from there on how you can improve and increase the kind of tasks which we are solving today. Okay. So now let me start with the very basic thing about machine learning and a recall of facts. Now, any kind of a machine learning is essentially, so majority of machine learning which is data driven, where you have some sort of data from where you are deriving your understanding about the problem and trying to come to a understanding of how to solve this problem. That would generally be taken from the whole perspective of statistical machine learning. And what it says is that it uses concepts of statistics and probability in order to actually come to a confident decision. So say that we are starting with this very simple thing called as a Bayes rule. And what this Bayes rule says is very straightforward. Given that you know what is the joint probability of occurrence of an event and a decision. So a decision is omega, an event is x, and you know what is the evidence of an event occurring, which is probability of x. You can estimate probabilistically, or you can probabilistically assign what may be the possible outcome. So an outcome or a decision is omega. So if say there are I'm looking at it from purely a thing that you have certain measurement x, and you say that based on the measurement x, I would like to see whether it belongs to object 1 or object 2. So your omega is object 1 or object 2. In case of images and objects, you can call them as class 1 and class 2. In case of medical images, we can make it even simpler and say whether it's say normal or it's abnormal. Okay, you can call this as malignant, benign. You can call this as tumorous, non-tumorous. You can call them as asymptomatic and symptomatic. Anything whatsoever you like. Now we are looking at a 2-class problem as of now. You can also have a 3-class problem. So it can be something like a normal tissue, benign tumors, malignant tumors, and these benign and malignant together can be classified as tumors or asymptomatic behaviors. Now, here, if you want to do that, then we can think of rewriting this even into a more simpler form, which may be something which most audience over here who have done some fundamental courses in say pattern recognition already know about. So if you have done some fundamental course in pattern recognition, you might know about this Bayes rule, where what it states is that this outcome part is what is called as a posterior probability. So posterior probability is probability of getting a certain class knowing what is the observation which you have or the evidence which you have. So given a value of x, assign a probability to a certain class which is omega. Now that can be derived from likelihood, which is essentially probability of a certain evidence coming that it is from a certain class. What it means is that I have a bunch of cancerous tissues and I have a bunch of non-cancerous tissues. So I make this measurement x on the bunch of cancerous tissue. I make this measurement x on the bunch of non-cancerous tissue, and then come up with a probability. And this is purely statistically defined probability. So we get down our histograms. From there we get a probability mass function, and that probability mass function is what we are doing. So in fact, I have slides where I will be showing you exactly how do you arrive at these kind of probabilities based on pure measurements which you do in experiment. The other term which is critical is what is called as prior probability, which is essentially the probability of getting a certain class. And then I have another thing which is called as evidence. So evidence is the probability of a certain x, which is an event, which is some sort of an event. It's also called as an evidence. Evidence comes from the fact that whether or not x is possible at all or not. So in case say x is some sort of a feature which you are measuring, and it is very unrealistic. So if x is not at all possible, then the evidence is going to be 0. And if evidence is going to be 0, then you can pretty much say that this whole thing becomes unsolvable, because whatever be the numerator over there, the denominator always turns out to be 0. Interestingly, I will also show at a point of time that whenever the denominator is 0, the numerator necessarily has to be 0, otherwise it will not work out. Okay, it's not so complicated to understand, but I will actually show it to you mathematically with a numerical example over here, and then we will get to the point like what do you do in case you encounter such a situation, and can we really look at solving that as well. Now let's look at this primary point on what happens in a decision. Okay, and I'm going to take this very simple example again, a bunch of slides which I've just pulled out from my classroom lectures on deep learning on trying to classify two kinds of objects, and I just kept two very commonly seen objects on Indian roads: cars and cows. You will always have them on Indian roads. The other thing is that both of them think that they dominate the road, both the cow and the car. The cow will not move even if there is a car, and the car also doesn't really move. The car doesn't care about anybody. The car will go at its own pace. So now, if I measure just two attributes, okay, x1 and x2, these are two scalar attributes about any object which I am measuring. So the object may either be a cow or a car, and the scalar attributes which I am measuring is shade of color, which is whether it's black or white, or it is some shade of gray intermediately. It may be brown, green, whatsoever may be the color, but if you map it back onto the intensity scale or the grayscale map, then you would find out certain shade of gray. And the y-axis or the vertical axis over here is defined by another scalar variable which I call as x2, and that is something which defines the length of this object. So it may be the head to tail length of a cow, or it can be the head to tail length of a car. Okay, from the headlights to the taillights for a car. So interestingly, you would see that most of these objects might have a bit of overlap. There can be certain cows and cars which will be almost of the same length. In general, a lot of these small hatchback cars are actually of the same length as a cow itself. and they are also almost the same kind of a grayscale intensity. Okay. Somebody has raised a hand. In case you have any queries, my recommendation is that you write it on the chat. I'm generally following the chat for any questions. So you can post your question in the chat and I will definitely answer it in the runtime itself. Okay, now that you have this kind of a scenario, what we are looking at is that by solving this kind of a posterior probability thing, you can come to a decision rule known as maximum a posteriori or MAP behavior. So what MAP does essentially is that for any given value of x, so when you are getting this any given value of x, what it means is that x lies on this space. X as the vector lies on the space of x1, x2, which are the scalar constituents of this vector. So if I am looking at a two-dimensional feature space. Now, as I keep on varying the value of x, I will be able to cover the whole of this feature space. And as I'm keeping on covering this whole of the feature space, I will get my posterior probability. Now, whichever class has the highest posterior probability, I will assign a decision in favor of that particular class over there. So this is really what we have to do. Now, once we are able to do, what we will be able to achieve is a certain boundary, which is called as the decision boundary. And what this decision boundary does is that any object, say below this decision boundary, is what belongs to cows, and any object above that decision boundary is what belongs to cars. That is what typically it does over here. Now, you look into any other kind of a two-class classification problem, say tumors versus non-tumor cases, tissues, or you can look into malignant versus benign tumors, and then you will also be able to see the same kind of a behavior as whatever you see over here. Now, this boundary is something which is of very pertinent interest. So, what is the order of complexity of this boundary is something which is given by how jagged and rough this is, or is it as simple as a straight line? If it's as simple as a straight line, which is just a line, just vertical or horizontal, then you can define it as a order 0 system. So you just have one constant value associated with one of them, and then it's order 0 polynomial which can define it. So these are also called as axis-aligned splits. In general, very popularly used within random forests as well. In the other way around, you can see these kind of very nonlinear looking structures over here, and these can be defined by a certain nonlinear ordered equation also. So that's what we have and where we need to really look forward and go. So this decision boundary is really critical, and we need to have a very deep understanding about it. Now, what happens as challenges with decision boundary is something like this. One of the options is you can have a lot of samples. Now, when you have abundant number of samples, then what happens is something like this, that you can get a decision boundary which can very tightly fit over here and give you a option that something on the left, basically it can very tightly divide the samples on two different sides of it into two different classes. And that's something which makes it really nice. So a situation when you have this kind of a scenario where you have lots of samples and they are pretty much well spread across, then your decision boundary which you get down over there is a very good decision boundary. In fact, these kind of problems are what are called as perfectly fitting problems. A perfectly fit problem, or a problem which is a good fit. A model is generally said as a good fitting model when you see that you have a very uniquely characterizable decision boundary and there are no ifs and buts around it. When you don't have so many abundant samples, then what can happen is this can definitely be one of the decision boundaries, but then this is not the only decision boundary. You can also see that this can also be another possible decision boundary. So you can see that there can be a nonlinear equation which defines it, or even a linear equation, order 1 equation which can define this decision boundary, and that will also work out pretty fine over here. Now, from here, if we get down to another point, which is about scarce sample, you have even more challenging situation over here. What can happen is, you can have this as one of the decision boundaries, but then say for a line, you have two variables. So a line equation can be written as x2 is equal to m into x1 plus c. So m and c are two different independent variables which will characterize exactly like what is this line going to look like, what will be the slope, what will be the intercept, so how far away from the origin it's going to be. So turns out that when you have very scarce samples in order to take a decision, then there can be many possibilities of this decision boundary which can occur over here. So this really brings a lot of problem in our lives, because you cannot ascertain a very unique decision boundary in some way by doing this. You will have a very tough time in order to find out which is going to be that unique decision boundary which will work out. Now comes an understanding about these challenges. So say that I am looking only at this likelihood, and now what I want to see is that if there is this kind of a decision boundary which is coming over here, then what is it dependent on? Okay. Now say that I have a decision boundary which looks like this, whose geometry can be defined by a cubic equation. Okay. Now if I ask you this question, that how can you tell that this will be a cubic equation? I just drew a line, but looking at this line, how can you tell that this is a cubic equation? Can somebody tell me? Just by looking at this line, how can you tell that this is represented by a cubic equation?
But certainly it is not linear.
Yeah, it's certainly not linear. It can be a quadratic, which is an order 2 equation. It can be cubic, order 3 equation, which I'm saying over here. It can be order 4 equation as well. But why do I say that it's a order 3 equation?
Characteristic function of x cube.
So I did not write the equation at all. I did not say anything about the characteristic function. What I've drawn is just a line, just a curve over here.
It is the probability you're starting with.
No. See, I've just drawn a curve over here, which is the decision boundary. Now what I'm saying is that in some way, this decision boundary is related to the, so whatever is the polynomial order which can define this curve of the decision boundary is also the polynomial order which is defining my likelihood. I will come to the point how it defines the likelihood. But as of now, assume that whatever is the polynomial order of the curve is the polynomial order of the likelihood function itself. Now I am saying, can you tell me, just by looking at this curve, how can I say that my polynomial order of this curve is cubic, as a result of which polynomial order of my likelihood is also cubic? So can you really see that in this particular curve, it's so I am getting some response that if x moves on step of like if x moves one step, then y will move by cube of x. But is that the thing which is happening?
We will have two reference points for this curve, and accordingly we will have a cubic equation.
I did not give you points. I just gave you curve. So how can you look at it and say that this will be a cubic? So think in terms of, I can give you a clue. So please think in terms of curvature of say any kind of a curve.
I mean, total number of curves which are there.
Yeah, not total number of curves, but curvature. How many times does a curvature change? Is there something?
I mean to say the same, sir. I mean same. Number of slopes.
We don't call it number of slopes. I mean, number of slopes will be a piecewise linear equation, but I am looking at a pure nonlinear equation over here. So is there something on the number of times the curvature is changing, which sort of like
Hello?
has a relationship with the order of polynomial?
Hello?
Yes.
Can I say something, sir?
Yeah, please.
Yeah. So we will have a 4 reference point totally, starting, ending point for the path that we are getting, upper one and the lower one. So 4 minus 1, we will have a 3 degree.
Okay. Then?
With respect to mathematics, I'm just explaining, sir.
No. My point is like from there, how will you get down the polynomial order?
Sir, it has two peaks. One is the lower peak, and the other one on the other side it has a higher peak. So two peaks, or some, it is varying 2 times. For that reason, it is.
There are two curvature changes. There are 2 points of inflection, as we call it. Okay. So I will give you a very simple example. Okay. So all of you know about an ellipse, which is a quadratic equation. So how many times within an ellipse is there a curvature change? Or say a hyperbola or a parabola. How many times within a parabola or hyperbola is there a curvature change?
4 or 8 in circle 8 points.
It's only once.
In circle 8 and in ellipse 4.
No, you need to look
2
into
times.
something in an ellipse.
2 times.
2 times.
An ellipse is basically a closed form about a symmetric axis, which is its reflection. So we are not going to consider the reflection. We'll have to consider the primary number of changes which have. So in an ellipse, it is only once. The same is what holds true for a hyperbola or for a parabola as well. You will have only a change which is once. There is curvature change which happens only once. So it has a quadratic order in those equations. If you look into this kind of a line, you have a curvature change which is twice. So you have one curvature change over here, another curvature change over here. So there are two curvature changes, which is a very characteristic thing about a cubic order equation. This is just about like looking into curves and telling like what may be an order. Okay, now what I was trying to explain you is something like this, that I said that whatever is the order of this line is the same as the order of the polynomial. Now, how do I make that statement? Okay. Now, something critical over here is that whatever is the order of the likelihood, that will be the same as order of evidence. And why that will come down is that your evidence or the denominator is basically equal to sum over the marginal product in the numerator. So your numerator is basically product of likelihood and prior. So prior is anyways a constant. It's not a polynomially defined quantity or something. It's a constant number, you will always get. So the prior and likelihood will have a product where whatever is the order of the likelihood, the polynomial order of likelihood is the same as polynomial order of this product. And then if you take a summation of these marginal products over all the classes which you have, then what you end up getting is your denominator, which is your evidence. Now, so if your likelihood is of polynomial order 3, then your evidence would essentially also be of polynomial order 3. Now, if I divide a cubic equation, cubic polynomial by another cubic polynomial, my resultant is also a cubic polynomial. This is again like straightforward first principle proofs. So my posterior probability is now going to be a cubic polynomial. Now what I did was, in order to get this decision boundary, I took a argmax. So from the order statistics problem, if you have a function like maximum and an argument over the maximum, that will also be a cubic polynomial, given that the input argument to this function is a cubic polynomial. Now I'm not going into much more mathematical detailing and explainers of these. These are from very standard math textbooks which you can get into it, but that's from where it comes down. So the shape is essentially something which is guided by that likelihood function, which is one of our key takeaways and what we are going to discuss more. Now, alternatively, you can also have this kind of a line which can define a likelihood, and that can be a quadratic polynomial, or you may even have a linear which can define this likelihood over there. The question is that, is there certain advantage which I gain, or maybe certain disadvantage which comes into play if I do not consider or maybe consider a cubic versus a linear? It's something like this, that instead of a cubic polynomial, if I take a linear polynomial, do I gain something? Is there some advantage in trying to find out the parameters of this polynomial or define the polynomial, or is there certain disadvantage? Okay, linear is predictable. I believe all of them are predictable. Given enough number of data points to you and enough compute power, you can always find out the best polynomial over there, which fits and creates that segregation margin. So can somebody tell me that if I want to fit a straight line, I just want to fit a straight line to certain data points, then how many free variables will I have to optimize for? How many free variables do I need to optimize if I want to fit a straight line?
At least one.
So what is the straight line equation?
Y equal to mx plus c.
Mx plus c.
Okay. So how many free variables do I need to tune over here? So in y equal to mx plus c, what are the dependent variables and what are the independent variables? Dependent variables as in like which things you can optimize and play around with, and the independent variables are what anyways you get as a
C is an independent variable.
No.
C.
In y is equal to mx plus c, if I give you a set of data points and I ask you that you fit a line to these data points, then what are the free variables which need to be optimized in order to fit that line?
X1.
M and C are the optimal.
Yes,
X1.
M and C are the two independent parameters which need to be fit. The two free variables which you need to fit are M and C. There are different ways of looking into an equation from a systems point of view. Here, my objective is what are my free parameters which I can optimize such that the straight line fits on a set of data points which I am giving. So in case of a linear equation, it's order 2. So I have two free variables which I will have to fit, and they are M and C. Okay. Similarly, if I have a generalized quadratic polynomial, then how many free variables do I need to fit?
3.
No, think about it. Generalized quadratic polynomial. A generalized linear polynomial is something which consists of order 1 and order 0 variables. That's why you got that constant C, because there was an order 0. So if I write down y is equal to mx plus c, then what I essentially wrote down is y is equal to m times x to the power of 1 plus c times x to the power of 0. So similarly, think that if I want to write a quadratic equation, then how many free variables will be there?
N.
Now what is that n?
3 variables.
A generalized quadratic. So can somebody write down a generalized quadratic equation? No. Order, if the polynomial, if you have a polynomial of order n, then you have n plus 1 number of free variables. No, that's wrong. It comes from combinatorics. What you are saying is wrong. Ax square plus bx plus c is equal to what? When we said equations,
Equal to 0.
with equality sign. Ax square plus bx plus c is equal to 0 is not a equation of x and y. It's just an equation of x. I have two independent points, x and y, which are always specified to you. That's the thing on which I'm fitting. I imagine this to be a 2D space, a 2D Cartesian coordinate system. You have some points given over there in x, y, and it's said like you come up with an equation. You have just said that okay, this is a quadratic equation over there, and then you fit a quadratic equation which will such that this curve will pass through all the points which are given to you. Then what will be that generalized form of quadratic equation which you are going to write? Okay, again give you an example of the linear equation. Your linear equation was y is equal to mx plus c. Okay, essentially what you wrote down is something like this. Y to the power of 1 plus c1 y to the power of 0 is equal to a x to the power of m into x to the power of 1 plus c2 x to the power of 0. Now if I reassign all of these things, then it becomes y to the power of 1 is equal to m into x to the power of 1 plus c1 plus c2 minus c1 or c2 y c2 x to the power of 0 minus c1 y to the power of 0. Now x to the power of 0 and y to the power of 0 are just unity, so it becomes c2 minus c1, which you can write down as c, and thus you get your line equation as y is equal to mx plus c. So in the same line, if I want to write a generalized quadratic polynomial, then what will that look like? So for a linear equation, you have y is equal to mx plus c. Now this whole thing I can also write as, let's say, y to the power of 1 plus c.
So would you please type the screen, please?
Yes, so I got the right answer, KPB. That's right. So you essentially have ax square plus by square plus cxy. So these are all my pure quadratic terms, plus dx plus ey. These are two of my linear terms which need to be necessarily over there, plus f, which is my order 0 term. So there is a x to the power of 0, y to the power of 0, x to the power of 0 into y to the power of 0. All of these together will contribute to another coefficient, which is my constant, which is f, and that is equal to 0. So now if you look over here, you have 6 independent coefficients, a, b, c, d, e, f. So you have 6 free variables which you will have to optimize in order to fit a generalized quadratic equation to a set of data points given in 2D space. So if you increase one more axis, say your system is no more, your space is no more a 2D space, but now you have a 3D space, things will, your parameters will appropriately keep on increasing over there. So you can write down a quadratic equation in 3D space and what it will look like. Okay. Now, similarly, if you go to cubic, I think it's about 16 variables which you need to optimize. So you can write down in the same format, generalized cubic ordering equation. You will have x cube term, y cube terms, you will have x square y, you will have xy square, you will have xy, you will have all the x square, y square, all of those things going down. Now, if you look at it, my point is something like this, that if I have two free variables, which are m and c, how many unique equations do I need to write in order to solve this and find out the value of m and c? So if I have a linear equation, if I say that my decision boundary is linear, it's a linear polynomial, order 1 polynomial, then I said that there are two free variables which will have to be estimated over here. Okay. Now what I am asking you is that if I have to estimate two free variables, then how many unique equations do I need to have so that I can estimate two free variables? It's two unique equations, simple linear equation, like system of linear equations, solvable system of linear equations. You need to have two unique equations. If I have 6 free variables to solve for, then how many set of unique equations do I need to write? So if I have a quadratic polynomial, then I will have 6 free variables, and then I will need 6 unique equations to be written. Now, if I have a cubic, then I will have 16 free variables, so I will need 16 unique equations to be written. Now tell me that which of them is a easily solvable problem. Like, is solving a system with 2 equations easy, or is solving a system with 2 equations easy? Or is solving a system with 16 equations easy? Which one is easy? So definitely solving a system with 2 equations is the easiest one over here. Okay, that's the reason why you would often find that we try to estimate or we try to approximate these likelihoods or anything in terms of the simplest of the polynomials which is ever possible. So we don't go to too complicated polynomials. We always like to have simpler polynomials on which this can be done. Now, the point is, standing on top of it, one thing we did identify is that a linear is the best way to go forward with it. So you just have to, and in fact, going down the line, I would show you that in general, most deep neural networks are just linear systems. They will always try to linear systems. I mean, not linear systems. They would try to approximate a order 1 polynomial. Okay, linear system is a controversial thing to say, because I just ended up proving that neural networks can never be linear systems. They are pretty much non-linear. Even if you have order 1 equations, you will still be a non-linear system over there. Okay. Now, the challenge comes something like this, that when your data is really scarce, and that's the problem which we are dealing with, where I will explain you like how that scarcity of data comes into play, and there are very interesting undertones of this scarcity of data, which I will show you. So this can be one straight line equation, which is x2 is equal to mx1 plus c. There can be other options over here. So if you look over here, between this line and this line, both m and c have changed. Between this line and this line, m is the same, but c has changed. Between this and this, your c is same, but m has changed. So there can be many options over there. And in fact, like all of them are good, because if you look over here, each of these lines has 100% efficiency in being able to split the data into both the sides of it. Okay. So here comes the problem that these are essentially what we call as ill-posed systems. So you never have a unique solution. You can have many possible solutions coming around over here. And that creates a huge amount of problem when you don't have a unique solution, but a lot of possible solutions. So where we have moved as of today in this whole field of deep learning is initially within whole field of AI, how it started, and that's the super field which we are looking at, was essentially what we call as rule-based AI. That is plain classical AI system. So it's something like when you use your air conditioner. So you set your air conditioning temperature to say 25 degrees centigrade. Then what happens? It turns on, it senses like what is the indoor air temperature. If it is above 25 degrees centigrade, then it will turn on the compressor. The compressor will keep on running till the temperature goes to 23 degrees centigrade. Once it senses that it's at 23 degrees centigrade, then it will stop the compressor. Like that, it will keep on monitoring this temperature rise. When the temperature again 27 degrees centigrade, it again turns on the compressor. So what you have is a 25 plus minus 2 degrees in which it is waving. And according to that, you would see that approximately a long-term average temperature within your house is going to be at 25 degrees centigrade. Now, that's what was classical rule-based AI and how air conditioners, refrigerators, they used to operate basically. If you have a unit which is based on standard compressors, not these inverted technology refrigerators or air conditioners, then you would see this thing. Now, from there, we came to this whole point of when we had these hand designed features, and then we came up to a learned decision, and then you look at an output. And in fact, I can give you this example. So right now I have an AC, which is an inverter AC. If you have bought an AC maybe in the last 2-3 years, most of the air conditioning units as well as refrigerators which we get these days, they are all based on inverter compressor technology, and it costs a tad bit more, maybe about 5% more than the classical one, but generally they have much more stable cooling characteristics, and the power consumption is also low, so people love it that way. Now, what it does is something like this, that instead of doing this +-2 kind of a switching, it keeps on constantly monitoring this temperature, internal temperature. Now, it's something like when you are riding a bike, so you have an accelerator, and you can, or you're driving a car, you have an accelerator or a gas pedal over there. You can press that gas pedal so as to, sometimes you press it hard, sometimes you relieve it, sometimes you put a brake, such that the speed at which you are going is constant over there. Now, that's the kind of a thing which happens over here with these inverter ACs, and in fact that is what is within classical ML. So what we are trying to do is that you keep on monitoring a lot of factors, not just your indoor temperature, your outdoor temperature, what is the rate at which your cooling was happening, all of this, and then come to a learned decision, which is essentially a control parameter which you give to this compressor over there, so that it makes a very linear cooling characteristics over there. It basically like a straight line. So if I'm looking at 25 degrees centigrade of a temperature, then it should be 25 ±0.5 degrees centigrade, which is much more soothing than this ±2 degree, because 4 degree changes is what it was experiencing in the earlier case, and 4 degrees centigrade is a pretty much discomfortable change in temperature, honestly speaking. From there, we came up to this whole new thing of what is called as representation learning. So this was, say, early 2000s is when we started seeing a lot of concept of representation learning. A very classical thing of representation learning where it gets used is JPEG image compression. So if you're looking at J2K, which is wavelet-based image compression, or even the newer age image or video compressions like HEVC, HEIC, then next-gen compression techniques over there, they are all based on these kind of learned decisions and learned features. So what it does is that what kind of features or what attributes of the original input it needs to store in order to be able to reconstruct it is also learned on the fly. So it's not like for every image which you compress with JPEG, it will store the same kind of an information. So if you look into J2K, you would see that two different images which were shot from the same camera with the same kind of a pixel. So you can have two images with 12 megapixel each. But based on what is present in the image, you would see the file size keeps on varying. And that happens because you learn a different set of attributes or features for each of them, and then have a decision on which features should I actually be storing, picking up and storing over there. Now from there comes this whole area of deep learning as we know today. And what it does is, not just it has a set of attributes or learned features, it also derives a set of hierarchical abstract features on top of these learned features and then stores them or takes a decision in favor to store them. So this is what is all about deep learning as we know today. Now, starting with the point of what we want to achieve in this one, and then this is again what I'm doing as of now is just a primer on machine learning and more of trying to objectify deep learning from the perspective that understanding these will make it much more easier for you to be able to grasp the concepts which I would be discussing later on over here. Now, any kind of a machine learning problem can essentially be divided into three sub-problems which you need to solve. And these are independent of each other. One of the main things which you need to understand is about the data. So given that you have a lot of data available to you, you are actually dealing with a solvable problem or an easy problem. It's not even a problem. If you have a lot of data, most of your problem is gone because now you can solve it out easily. If you have less amount of data, that starts in all the issues, all the challenges, that it's not so easily solvable. So the order of complexity keeps on increasing as the number of data points keeps on decreasing, or the number of available data in your training set, it decreases. The next part of it is a model selection side of issues. So in model selection plane, what it does is that it's really easy to solve a linear model and it's really tough to solve a cubic model over here. So the order of complexity keeps on increasing as we go from a linear to a cubic kind of a polynomial. And the other part is what we call as the control plane, or this is where, given you know about the data, you have a data which is static, you have chosen a certain kind of a model and you want to optimize, then how do you really very quickly fit the free parameters of this model? So how you choose all the free variables in that model in order for the model to behave in a way such that it fits the data. All of this part is what we call as the control plane. Now the simplest of the control plane optimizations is what is called as maximum likelihood estimation, or is just a probabilistic method. So it just essentially solves out the base rule over there in order to do it. Okay. Now that's not the easiest one. There are challenging ones, and the next best approach is what is solved using mean square error, and that's the approach which is used in regression analysis. So you essentially try to minimize the mean square error. There are problems which can not necessarily be solved using these two, and in fact, like in today's world, we see a large number of problems which require the use of something which is called as a perception loss, and that perception modeling is something really, really critical. So we are looking at control plane of the problem where we need to come to much more refined technologies, and I will be telling you exactly what is this perception modeling all about and what a perception loss actually means. Now let's look into the first part, which is the data. Now, data is just what arrives to you. You don't have much of a control of it. I mean, most of us don't have it. Some of us, if we want to design experiments in order to collect data, yes, there is this whole field of study called as design and analysis of experiments. And you need to understand about experiment design when you are collecting the data. And all of this is a back and forth thing. So you'll have to get back to your understanding of the model, how many unique equations you want to write. And in order to be able to write a unique equation, ahead of time, you will have to predict what should be the characteristics of the data which will let you write those unique equations. The only issue is that until you have the data, you cannot write the equation, and until you write an equation, you can never say like exactly how it is easy to whether that equation is solvable with the data or not. So here comes a problem. Say that I am looking into classifying WBCs in microscopy images. I may not have a lot of images available to me in order to do this one. So one of the ways I can do is I can actually start looking at augmenting the data. So one way can be I can rotate the data. I can do a flip operation on the data. This can be left, right, flip, up, down, flip, any of them. Because a rotated version of a cell is still the cell of the same pathological nature. But then for a model which might be seeing them, the visuals changed. Like the thing what you saw in the earlier case on the left comes now on the right, or on the top, whatever you saw, it comes on the bottom. And then if you rotate, then there is these rotations. Now pathological nature of the class of the cell doesn't change, but definitely X has certain change over there. Some microscopic small perturbations are what you are creating. Now by doing that, you will be able to shift a data space of sparse data, which looks like the one over here on the top right corner, to something which looks over here, by way that you will be cloning these data points. So these data points will be cloned by way of these kind of some augmentation operations which you do. Necessarily, you cannot guarantee that every time you clone these data points through these augmentation operations, they will lead to unique data points. A lot of times they will be non-unique data points as well. Now comes the whole point that this whole task is something which is generally called as an art of data augmentation. It's not majorly a science, because if you had rule-based things, then you can end up writing a rule like this, a flip up down for a cow. But you know that a flipped up down cow is something which is wrong. So if you are training a model with this kind of a cow model in the augmented data set, then you actually augmented, and your augmentation process injected a very illogical kind of a data. So an evidence associated with an up down cow is with this kind of a cow whose legs are up. The real world evidence is zero. You will never see a cow like this. You can see a cow lying down, but never like its limbs which are raised in air. So this is about all of these illogical samples which can accidentally get injected into your system. So we'll try to see that such a thing never occurs. Now, the next option which you have is to look into these kind of model selection problems. So over here, we did say that the easiest is to actually solve with the linear equation, but the point is that if a model does not become inherently a linear model, not an order 1 equation, then how do you really solve it out? Now, one way is say that what you learned out a certain set of features, and the features which you saw on the feature space is something like this. Now, definitely the learned decision which gets learned over here is a quadratic polynomial, and it's say an ellipse. This is definitely an order 2 polynomial. The point is, can I do certain transformation by injecting another layer, which is this now abstract layer which is present inside neural network. So this brings in the whole concept. So what a deep neural network essentially tries to do is it puts in more and more number of layers such that a transformation from one layer to another layer will make this data more and more linear towards a linear thing. So if I have some say order n equation and I have n number of order 1 equations cascaded one after the other, then I am going towards the last phase where I am able to linearize the presence of the data, such that this decision boundaries and everything is just an order 1 equation, and the number of free variables I will have to solve for order 1 equations is much lesser. So the guarantees on performance, the bounds on performance become much more guaranteed over here. Now here, if I want to do this, I want to convert this to some sort of a representation like this, such that my decision boundary now becomes a straight line. That is essentially the purpose of this learned abstract feature layers. Now, how you do it is all what comes into deep learning. As in over here, it's very straightforward. So if your abstract feature over here tries to model something which makes something like a Cartesian to a polar domain conversion, then you would see that you will get down this kind of a straightened decision boundary coming out very easy. The next problem which we look into is what is called as a control plane of the problem. Now here, when we look into the control plane, the easiest of the ways is to do a maximum likelihood estimation. That's just a probabilistic way of solving it out. But then it's not so straightforward, and sometimes you might have problems like this. So I want to train, say, a neural network where I give an input of a hand-drawn sketch of a house or something, and then I ask this neural network that can you render a photographic equivalent of this one, and say it renders like something like this. Now, between the two images, you will have a low mean square error because the color of the pixels at the exact location of the input and output are more or less same. There is some noise over there which got added because of this transformation. But then, while the mean square error is low, the perception loss is very high. So perception loss is something like this, that does the output look like a photograph? Does it appear to a standard human as a photograph, as a camera photograph? No. So my perception output over there is going to be really high. And this is a very critical problem which we need to look into it. So my perception loss is very high over here. The question comes down that my MAC is low, but my perception loss is high. On the other side of it, if I have an image which is produced like this, now the perception loss is very low because this looks very much like an output from a camera. The issue is that the pixel by pixel positioning, the difference of the colors and everything, that's also very high. So the mean square error is very high over here. So while my mean square error increased, my perception loss decreased. And as a result of which, you would see that perception and distortion, or mean square error is something like a distortion error. So point to point, what is the amount of distortion between signals? These are pretty much opposing in nature. Now here comes the whole issue that is there a mathematical form of actually representing perception? And that is a very, very challenging problem to address. So say that I am looking into addressing this one. How we in the community try to achieve this one is using something called as a discriminator neural network. So the idea is something like this, that you have a neural network to which you are going to feed a photograph or a generated image. And then you ask this neural network that when I give you these images, can you tell me whether this was an actual photograph or this was generated from a neural network? Now, initially, when the generated thing from the neural network looks very different from a photograph, the this discriminator can very easily say that no, what you're feeding me is a generated image, it's not an actual photograph. The only way you can start making this discriminator believe that whatever I am feeding from a generator is also a photograph, only when the generated one starts looking like a photograph, as in over here. And once you are able to achieve that, so that's something which we do in adversarial learning. So I will be coming to them as well. But once you are able to do that, then this Sketch2 Photo CNN that can very easily start generating things which start looking like a photograph. Now that will be, and then obviously this cannot be achieved by minimizing the mean square error, because that's definitely not what is a doable thing over here. So we'll have to do it using some other way, and that's again done by an approach which is called as an adversarial attack within learning systems. I will come to that, but once you are able to achieve it, definitely you have a way of learning a loss function itself. So in earlier case, a mean square error or something was when you had a very well-defined mathematically defined loss function. Here we are saying that we don't even have a pure mathematical definition of the loss function. So what I'm doing is I am learning a perception loss, and that makes it really nice over here. Now that brings me to the point of this first paper. Now I have roughly about 8 minutes before we end up the first session. I will try to at least get you a substantial introduction to what we have in this particular paper. Now say that I am looking into a task where I am being given with a retinal image, and my task of this neural network over here is to perform full-scale semantic segmentation. So full-scale semantic segmentation as in my neural network should be able to identify anatomies like the blood vessel, the optic disc, and the optic cup within this image, as well as find out pathologies which are like edema, soft exudates, or hard exudates, which I see over here. So I want my neural network to be able to do all of them. The challenge which comes out is a weakly labeled data challenge over here. Now, weakly labeled data issues are manifold. There are different definitions which come in terms of weakly labeled data, and I'm going to speak about weakly labeled data in terms of where your data sets, there is no single data set which has all the class labels associated with it. Okay, so now say, and this is a true case. I mean, there are 3 data sets which we are looking at. One of the data set has annotations only for blood vessel. Another has annotation only for blood vessel and optic disc. Another has annotations for only hard exudates, soft exudates, microaneurysms, and hemorrhages. It does not have annotations for any of blood vessels or optic disc. Now, given that, as you look into these images, by now you do understand what are optic disc and blood vessels, because I had given you an anatomical reference in the first case. Now, even if the object is not marked, say in dataset 3, the blood vessel and optic disc is not marked, does not mean that dataset 3 does not have any blood vessel and optic disc. It is still there. So that anatomical structure is present. It's just that it is not marked over there. So the point is that the data or the class is present in the input, but it is not annotated. So that's where the weakly labeled thing comes down. Also, in the second data set, in the first data set, there is no pathology present. But in the second data set, there are some pathologies. I mean, I can pretty much see that there are soft exudates and aneurysms which are present, but then it is not marked. Does not mean that the dataset 2 is perfectly healthy over there. So here the challenge was like, how do we really, how should we be able to integrate all of this information together in one shot? Okay, that's where all of this challenge comes into play, and we need to figure out a way of addressing these challenges. So what we came out was this kind of an approach over here. Okay, so the idea is something like this, that given an input image for which you know what are the different classes of annotations which are present. Now, I have some C number of objects which I need to annotate over there. Now, dataset 1 may have only one particular object annotated. Others are not available to me. Dataset 2 might have only 2. Dataset 3 might have some of the 4 or 5 of them available over there. Say that my C is 6 over here, just as a representative purpose. Then what my semantic segmentation network is supposed to generate is a map of whatever it sees. So if it sees a blood vessel, it will have one map of blood vessel. If it sees an optic disc, it will have a map of optic disc. If it sees optic cup, it will have that, microaneurysms, etc., etc. Say all the 6 classes, it will show it out over there. This is what I expect this neural network to do. Now, in order to train this, I will have to make use of 2 such learnable loss functions, which we called as discriminators 1 and 2. Okay. Now, some of them will be adversarially attacking the semantic segmentation network. Some of them will not be. I will in fact like show you what an adversarial attack exactly means over here. So you don't need to come with that preconceived notion of a GAN or anything. I'm exactly going to tell you what it is. There will be one of them which is going to assist the network, one of them which is going to attack the network and make it powerful. So it's like you have a kid at home and then the father is scolding the son or the daughter and the mother is always pampering. So you give some two opposing kind of treatments to them in order to that the kid is becoming much more resilient and is able to understand all of this. So, I don't know, somebody is constantly raising their hand, and I don't know what's happening.
Dear participants, Saranya Umapati, may I know the issue, please? Saranya Umapati.
I think she might be having some technical issue. So one other option, I mean, a lot of people are raising their hands, I see. So one option is like whoever has raised a hand, if they are facing a technical issue, you can log them off the platform and they can again log in themselves.
It's a technical problem only, sir. Otherwise, these many hands won't get raised.
Yeah, it looks like somebody is constantly poking over there. Maybe there is a kid present and the kid is doing that.
Yes, sir. Okay, sir. Carry on, sir. For another, we have a session up to 35. Yeah.
So now here, the point which I wanted to make is that how do you really create these discriminators and do it? Now, on a this is a slide which is more of on a philosophical note, exactly of what I want to achieve. Let me mute myself. Let me reduce my audio. Otherwise, that sound is disturbing me a lot. Yeah, I mean, host can actually remove that participant and then you know what is the issue.
Okay, sir.
So now, when I want to feed this data to these discriminators, what I want to do is something like this: that the discriminator 1 is supposed to look at the output over there, whatever is getting output generated tensor, and then say like which is the class which is present in that. So whether there was optic disc or blood vessels or whatsoever, which is present over there, and it can look into that and tell. Okay, that's for discriminator 1. Discriminator 2's job is that if I give it a feed, a combined feed of the original input as well as the segmented output, then can it compare on a case by case basis and say that which of them is original and which of them is not original or is a synthetic, which is an outcome of the semantic segmentation network. Now, these two things are essentially perceptual in nature, and these two kind of perceptions will be able to help the network learn in order to merge information from multiple data sets to solve this problem. Now, coming to the first part of it. So the first part anyways is always a structural loss understanding part. So what we wanted to do is something like this, that given input image to the semantic segmentation network, it's going to generate a set of output tensors. Okay, so if I have 6 classes, then I need a 6-channel tensor over here, definitely coming in. Now that I have this 6-channel tensor, I have one channel associated with each class. Now what I'm doing is, on the input data set, there may be a, so on the input data image, there may be a class which is present. Say aneurysm is present in the input, but in the input image, but in the data set it's not annotated. Okay. Now, since it is present in the input image, my network will obviously be predicting it in the output. The issue is that although it has predicted in the output, but it does not have a reference to say that where it's present. So the ground truth is not available for a certain class. It's able to predict, but the ground truth is not available. Ground truth is available for some of the other classes which it's able to predict. As in, if you look over here for the first image, you would see that I get down my ground truth is available, or Y, which is my ground truth is available only for my blood vessel and my hard exudates and soft exudates. But my prediction over there gets me blood vessel, optic disc, optic cup, some edema, hard exudates, soft exudates, all the 6 classes. But if I try to find out like what will be the loss function between them, it's going to be tough. So what I'm going to do is I will compare the performance of only those classes which are annotated in the input and give a benefit of doubt to the network. It might have predicted some classes which are not annotated in the input, but I'm not going to penalize on them. I would say though, okay, it's not annotated in the input, so I don't know anything about the classes because it's not given in the input. So I'm not going to penalize you for giving me some extra. So this is something like there is a student who is writing a lot of things. So say you had these question papers where you give 6 questions and you ask them to write any 5 questions out of 6 questions. There would be a lot of students. I mean, I was one of them who used to write down all the 6 questions. And it was very simple because I mean, most of the time I was bored. In maths paper, I mean, I was pretty much bored because 5 questions is something which you will anyways finish up very fast. It doesn't take you 3 hours to solve 5 questions in maths. So what do? So all the remaining ones also I used to do it. Otherwise, they don't let you go out of the exam hall and you are anyways bored. You come home early, then also there is a lot of questions again from your mother, like why did you come home early? Did you check, double check, triple check, all of this? So my way around it was like I used to solve the whole question paper. So you are never in confusion that did it ask you to solve 4 or 5 over there. So the point is that if you are not penalizing a student for that, it does not really hamper in any way. And in fact, like you will see that a student becomes better and better. So in fact, the network over here is also becoming better and better because it's predicting. You are not penalizing because you don't know exactly what is the nature over there. So in the second image, you see that it did not have the ground truth of the blood vessel, optic disc, optic cup, but it had it only for the say this edema, hard exudate, soft exudate. So it's predicting only for them. That's over here, that this summation over binary cross entropy for wherever the original class is not equal to null. So wherever you have annotations, it's going to do only for that. So this is one way where you are just looking only at pixel to pixel understanding or just a structural error point of view. From there, we need to get into the other part of the problem where I want to use these adversarial losses in order to work out. Now, what did I say in the first one? The first discriminator's job is to find out in the output over here, whatever it's predicting, just looking at the output, it has to say what is the class of the object which is being shown in the output. Now, what it can do is, if I have this as a fixed order of 6 things, the first one will always be a blood vessel, the second one is always going to be an optic disc, the third is always going to be an optic cup, then this discriminator will start behaving in a way that even if there is one pixel which is high in that particular channel, it will say that that class is present. It does not need to understand exactly what is the shape of these things. Okay. And we wanted to actually be able to look at the shape, size, and appearance of a blood vessel and then say that it is a blood vessel. So in order to be able to do that, the idea is that you use a very simple technique which is called as a shuffler. So what I'm doing is, I have my original image, so my RGB channels of the original image, which I'm keeping it intact. But for the other predictions, because I need to give a reference to it in order to compare it. For the other one, what I'm doing is I'm just going to shuffle these channels. And every time there is a random shuffling which is happening. Every single epoch, every single call of this function, there will be a random shuffling. And what this will make you do is, it's just like if you teach your kids at home, then you would say that if you are asking them to identify alphabets, initially it's like A, B, C, D in the same order. But after some time, when they have gone from A to Z, you would start giving them shuffled alphabets, like some randomly drawn alphabets, not necessarily in the order of how they come. And this is to see whether they are memorizing this sequence or they are actually able to identify the alphabets. And then comes down puzzles, then comes down spellings and everything, and then so that people can recall. So this is exactly a tough problem which we want these discriminators to do, and that can be possible only if I'm assigning this kind of a shuffling thing over here. I will use a couple of more minutes if you let me use that, and then I can finish off this paper, and then the remaining 3 papers is what I will come back after the lunch break, and then we will do. Now, in the discriminator 1, the whole job is to find out the classes. Now, what I did say is that in the predicted output, in the input, a class may not be marked. Does not necessarily mean that the class is absent. So what we did was we actually manually went through all the images, showed it to a ophthalmologist, and just took a binary input over there. Like, is this class present or absent? Present or absent? So we created a separate vector of presence of classes, which is called as N1. The job over here is to see that if the discriminator is able to say output which is the same as N1. This is what it has to do. So it has to, but it is presented with shuffled order of these classes in the output tensor. That's why it has to learn exactly like what should a blood vessel look like in order to be able to tell that it is a blood vessel. Okay. Now you can get some initial idea of how this one from a motivation from this particular paper from JMLI about domain adversarial training within neural networks. The next job was to get this discriminator 2 to work, and what its job is that it does a standard adversarial loss function over here, which is provide it with the input tensor as well as the output, with a clever thing that this output over here we mask it. So if a certain class is not given in the input, we will mask that in the output itself deliberately. Otherwise, what will happen is what you are asking this discriminator is, I'm giving you 2 inputs. You tell me like whether the first one is synthetic or the second one is synthetic. Simple. Synthetic is whatever is the output of the segmentation network. Now, if I don't mask the input ones, like whichever is absent in the input, I make them absent in the output. Then what it would do is, wherever it sees a bunch of tensor where all of these things are present, it would say that is synthetic. That is always synthetic. Because it knows by now, after training this network, it would have known that my input is always going to be sparse. It will never have all the classes present together. So the only way I can do is, I will blindfold things appropriately. So whatever is blinded in the input, the same will be blinded in the output. So now it makes it tough. So now it has to actually compare. Okay. Now, once we are able to do all of this, what do I want to achieve? Is something like this. I want this semantic segmenting neural network to be such that the segmentation loss is minimized. So what I want to do is, I will backpropagate the direct gradient of the segmentation loss through this network, because I want to minimize the segmentation loss. Great. Along with that, I want to do something with my discriminators, or what I call as my adversarial losses. Okay. I want to make my discriminator 1 more and more powerful. So discriminator 1 should become more and more powerful in being able to accurately say, by looking at a binary mask, which particular class it belongs to, whether it's blood vessel or it's optic disc, optic cup, aneurysm, whatsoever. So the objective is to minimize the loss of discriminator 1. So accordingly, by that loss will also be backpropagated through my semantic segmentation network. On the other side is discriminator 2 will become, if discriminator 2 is very powerful and its loss is very less, then it will be very easily able to say which is synthetic and which is manual. The point is, I don't want it to be so. I want all of my synthetic output or whatever is getting produced from the neural network to be so realistic, close to the manual one, that discriminator 2 should start making mistakes. So the loss of the discriminator 2 should increase, and only when discriminator 2's loss increases, I would say that the semantic segmentation network is behaving good. So the semantic segmentation network's objective is to adversarially attack the discriminator 2 and maximize its loss. And that can be done only if the negative of the loss is backpropagated through the negative of the gradient of loss is backpropagated through the semantic segmentation network. And that is what gives you this adversarial loss function over here. There are 2 balancing factors, alpha 1, alpha 2, which are very standard for loss balancing within these kind of dynamic structures and dynamic losses within neural networks. And you can read more about those things in at least our paper, as well as the codes and some of the other standard things I will say at the end of it, standard lecture notes and videos which I have, where you can understand about what is that alpha 1, alpha 2, how does it really behave and act over there. So as a result of it, finally comes down the curtain raiser. This is what we have. So on the top over here, this is the image from the drive data set, and you would see that only blood vessel was marked, so we could get very accurately blood vessel. But optic disc which was not marked, we also got that. There were no pathology, so we did not get anything. The second one is from IDRID, where blood vessels are present, but it is not marked. All the other pathologies, optic disc, everything is marked. So that comes out pretty good. Along with that, we are also able to see these blood vessels which come out over there. And that's very interesting because now you would see, because we now have a very good understanding about, say, blood vessels and optic disc, optic cup from other examples from other data sets. So it stops making these kind of systematic mistakes, which are trained only on one particular data set make. So systematic errors starts getting reduced over there. So that's where I would stop with this one. Next, I would come to this whole thing of how we did super resolution microscopy in the presence of weakly labeled data and with very weak examples available. That's something I will take after the lunch break so we resume at 2:30 if I am sure about it. So I will just stop over here and we can go for lunch break, and I would request the coordinator to just circulate like what's the next timing of the session and everything.
Thank you, sir. Dear participants, we will have a lunch break, and we will meet again at 2:30 p.m. and I will share the same in the WhatsApp group also. Thank you. Have a nice day.
So it's going to be the same link, I believe.
Yes, sir. Same link, sir.
Okay. Thank you.